Hi, everyone, and welcome back to Psych 3510 for Chapter 8, where we will introduce and then discuss bivariate correlational research. So, in this chapter, we're going to discuss, like I said, bivariate correlations, talk about what they are, when we use them, how they relate to association claims, and then we're going to sort of investigate how we interrogate those association claims. So if someone makes an association claim, what are the questions you should ask about their methods and about their results so that you know whether they have a good claim, a well-supported claim, or a weak claim, a bad claim. So what is a correlation? That's the first place we need to start. Correlation is the statistic we use when we have two measured variables that we need to statistically compare to one another. And this produces an association or an association claim. So an association claim argues that one level of a variable is associated with a particular level of another variable. So a couple key points here. One, association claims, and then the statistic of a correlation involves two measured variables, and we are not making a causal claim. We're simply saying that these two variables are related to one another, not that one causes any change in the other. And that's a really, really important distinction here between association claims and causal claims. Association claims are a relationship. Causal claims are a direct cause and effect. So an association claim is stating that, something is going on. These variables are related to one another, but we're not confident enough to make a causal claim. And we probably did not engage in the methodology that would allow us to make a causal claim. Because we only have two measured variables, I didn't do anything in the world, right? I'm not creating groups with a manipulated independent variable. I'm simply assessing already occurring behavior in the world. And if I'm assessing already occurring behavior in the world, I typically don't get to make causal claims because I don't know what else is going on. So, for example, if I claimed that your GPA is correlated with your income after graduation. So the higher your GPA, the more money you make after graduation. The lower your GPA, the less money you make after graduation. I'm not claiming that your GPA causes your income to be higher. I'm just saying they're related to one another because there's a whole lot of other variables that are going to play into both your GPA and your income, such as the field that you're in, right? You could have a 4.0 in a field that tends to have lower pay versus, a 3.4 in a field that has really high pay, like, computer science or chemical engineering or something like that. So when we say that there's an association, we're saying that GPA and income are related, but we can't go that next step and say that GPA is causing your income. And so when we make these association claims, again, the statistic that we use is called a correlation. Now, we can visualize these relationships using what are known as scatterplots. Here's a scatterplot with some data about relationship longevity on the y-axis. So the higher up we go, the longer a relationship has lasted. And here on the x-axis, we have amount of expressed gratitude. How often you tell your partner that you're thankful for them, right? That you have gratitude for what they do. And so we can see, in general, on average, the more gratitude you express, the longer the relationship. So we have what we call a positive association or a positive correlation between expressed gratitude and relationship longevity. Now, the data aren't perfect, right? There's some sort of messiness, right? There's variability in this relationship because the lines are sort of spread. It's like buckshot out of a shotgun, right? There's some messiness to it. It's a little bit all over the place. And that's because humans are messy, right? Humans do not perfectly adhere to exact relationships, right? So if we sort of eyeball like a line of best fit to these data points, we might come up with a line that's like somewhere right here where I'm tracing my fake laser pointer. So if this is my line of best fit, we can sort of follow that orientation, and that orientation tells us that as one increases, the other increases, right? So that's what we call a positive association. As one variable increases in value, the other variable increases in value. As one variable decreases in value, the other variable decreases in value. They move together. Notice again, we're not making a claim about this causing one variable causing the other variable. It could be the case that the more gratitude you express causes the relationship to be longer. It also could be the case that couples who have been together longer learn to express gratitude better, right? So it could go the other direction. The causal relationship could go either way. Also, there could be other variables. There could be these other third, fourth, fifth variables out there in the world that are exerting impact on these variables, but we didn't measure them. And so we don't know what they're doing. And so we're less confident. And that's why we don't make a causal claim. There could be other relationship variables that we didn't measure that are exerting influence. And because we are naive to potential other variables, then we are less confident about this relationship. And so we stay at the claim of an association. We do not take the step to a claim of a causal claim. So positive association or positive correlation. We also have negative correlations or negative associations. They are oriented in the other direction. We can see if we drew a line of best fit here, then it would be, the opposite direction. Its orientation is different. In a negative correlation or a negative association, as one variable increases in value, so here as frequency of multitasking increases in value, skill at multitasking decreases in value. So as one thing gets bigger, the other thing gets smaller. That's a negative association. You also will often hear this called an inverse relationship because the variables move inversely to one another. And then, of course, you can measure an association where the variables are unrelated to one another. So here we have childhood weight and the time when your family eats dinner. They're uncorrelated. They're not associated with one another. And so there's no perceivable relationship here. It's just sort of random. It's literally buckshot, right, up against the wall. Again, I will repeat it as many times as I have to. Correlation does not equal causation. If you learn anything in this class, by God, it's going to be this statement. Just because two variables have a relationship with one another does not mean that one of those variables is causing a change in the other variable. A nice example, I'm having a deja vu moment that we talked about this example previously in the class, but who knows if that's real or not. So forgive me if I've used this example previously in the class. Also, as a side note, deja vu is a really interesting area of study in cognitive psychology. People do study deja vu. It's a real area of study because it tells us something about both memory and what's known as metacognition. So thinking about your own thinking, which is a really important area of cognitive psychology. So If you're interested, you can actually go read scientific literature on the experience and implications of deja vu. Anyway, here's an example that illustrates that correlation is not causation. So we find that ice cream sales increase as crime rates increase. We would be remiss to conclude that the sale of ice cream is causing crime rates to increase. What's actually happening is that as temperature rises, so during summertime, people buy more ice cream and they also commit more crimes. So the causal variable, so to speak, here is not ice cream nor crime rate. It's actually temperature. It's this potential outside third variable that's sort of surreptitiously coming in and influencing the relationship that you are assessing. So let's take a look at some sort of what data might look like for a bivariate correlation. Remember, this is the statistic we use to test association claims, where we have two measured variables. So what this correlation allows us to do is to statistically evaluate the degree to which change in one variable is associated with change in the other variable. Now, again, important to keep in mind, we cannot have categorical variables like gender or race or ethnicity or religion, things that put people into bins, right, into groups, are not variables that we can use in a bivariate correlation. We need variables that provide us basically either interval or ratio data. So numbers on a continuum, right? We need variables that provide us numbers on some continuum where you can score a 47 or a 58.2 or a 9.3 or a 1, right? Variables like that. So here we have data from a number of people, right? So person A, person B, person C, all the way down to person Z. And from each individual, we have measured their score on overall well-being, and we can see the scores here. And then we have also measured the percentage of their conversations that are rated as deep talk. So basically, not small talk, right? Like, hey, how's the weather? But deep talk, meaningful, emotional maybe, or intellectual or serious or important conversations, right? The percentage of a person's conversations rated as deep talk. And if we have these data, what we could do is we could ask the question, is well-being associated with percentage of conversations rated as deep talk? Such that we might be able to make the claim that the more people engage in deep talk, the higher their well-being, right? Or the more that people engage in deep talk, the lower their well-being, right? It could be the case that talking a lot about serious matters makes you depressed because serious shit is depressing. Or it could be the case that talking about serious stuff, makes you feel better. So this is what data would look like. This is what variables would look like that we could use in a bivariate correlation. Now, as I mentioned before, we cannot use categorical variables. So if one of the variables is categorical, and we might look like this. This is a different research question here. We have our participants, right, A through Y, and we ask them a question, where did you meet your spouse, either online or offline? So that's a categorical variable, right? You're either in the bucket of online or you're in the bucket of offline. Then our second variable is a measured variable. It's a continuous variable, marital satisfaction. So the question we could ask here is, does marital satisfaction differ based upon where you met your spouse, either online or offline? So this is still an association claim, because we didn't manipulate online versus offline, right? I can't take that independent variable and force you to meet someone online or force you to meet someone offline. I'm just assessing already occurring behavior, but it's a categorical variable. So let's think about what that would look like if we graphed it. Right? So here we have the bucket of online relationships, and here we have the bucket of offline relationships. And so they fall into this straight line going up because they all have the same value on the x-axis, right? You're either online or offline. There's only two possibilities. And then on the y-axis, we have variability. We can see the variability in marital satisfaction. So if we were to graph or do a scatter plot of a one categorical variable and one continuous variable association claim, we essentially end up with a bar graph, right? That's what this is. It's a bar graph. We could just take the average for each group and represent it like this over here on the right. This makes much more sense to do right here on the right than here on the left. Here on the left, it gives you some sense of the variability, and you will sometimes occasionally see people do this, but generally the more acceptable way to display this information is in a bar graph here on the right. If you're doing this style of experiment, then you would require a t-test. You've already seen a single sample t-test in this class. There are others, which you will learn in Psych 3530, but you would not use a correlation because a correlational test requires two continuous measured variables. And here we have one continuous measured variable and one categorical variable. So we cannot use a correlation. We have to use a t-test. Just a quick aside, there are multiple types of t-tests, three main varieties: a single sample or one sample, which you've already seen, and then dependent or independent, which you'll get into in 3530. We will not get into those here or this semester. Okay. So now that we've sort of established what a correlation is, how it relates to an association claim, we need to start practicing or learning about how we describe that association, right? It's not good enough to say there is an association. We need to be able to describe, is it a positive? Is it a negative? Is it no association? But then if there's a positive or negative association, what's the magnitude of the association? Is it weak? Is it moderate? Or is it strong? Because just because two things associate doesn't mean that that association is equivalent to all other associations, right? There are variables that are kind of related to each other. There are variables that are related to each other. And then there are variables that are strongly related to each other. We need some way of assessing that difference. That's what a correlation does. It's going to produce a statistical output that will allow us to assess that difference. So, a correlation or a correlation coefficient is denoted by the letter R, an italic R. R can vary from negative 1.0 all the way past 0 to positive 1.0. So between negative 1 and 1. That's where correlations live. When you're at or close to the 0 point, it means you have no relationship. So 0 means, 0 for a correlation means the lack of a relationship, the absence of a relationship. As we move out from 0, then the correlation and the resulting relationship becomes stronger and stronger and stronger. So what we're really looking at here is the absolute value of R tells us the strength of the relationship, And the sign of R, whether it's a positive number or a negative number, tells us the directionality, that positive versus negative thing that we did a few slides ago. So the absolute value of R tells us the strength of the relationship. The sign of R tells us the directionality of the relationship. So, for example, a correlation of negative 0.85, negative 0.85 would be a strong negative correlation, but it's equally as strong as a correlation of positive 0.85. It's just that the negative correlation means an inverse relationship. It as one variable goes up, the other variable goes down. And the positive 0.85 means they move together, right? As one goes up, the other goes up. As one goes down, the other goes down. So we have some guidelines for interpreting the size of R from an incredibly famous statistician named Cohen. Anything around 0.1 is considered small or weak. If it's below that, then it's really small and no relationship. If it's around 0.1, we're talking small. If we're around 0.3, then it's maybe a moderate relationship. If we're around 0.5, then we consider that a large or strong relationship, especially in the behavioral sciences. So when you're dealing with people and behavior in the real world, as I've said many times, people are messy. People have variability. Things happen to people that make things messy. And so very rarely do you find a super strong correlation in behavioral sciences, in the 0.8, 0.9 magnitude. Those are quite unusual when we're looking at complex human behavior, because complex human behavior has a myriad of relationships and causes. It's messy. When you're looking at more basic or concrete things, so if you're looking at, something in the business world or with economics or in chemistry or ecology, those things can be a little stronger because they're just kind of less messy than humans sometimes. But in general, 0.5 or negative 0.5, right? We're talking about absolute value, or greater means a strong correlation. 0.3 or negative 0.3 means a moderate. 0.1 or negative 0.1 means small or weak. So just, again, think about correlations as being on a continuum. In the middle is 0, and 0 means no relationship. And then as we move out from 0, the relationships get stronger and stronger and stronger and stronger, all the way to 1 and negative 1. And that's it. They can't go beyond 1 and negative 1. The way the math works is the statistic is constrained to that continuum between negative 1 and 1. So, if we were to look at this scatter plot, we're going to describe this as a lack of correlation, right? Basically no relationship. But if we look at this scatter plot, I want you to take a second and think for yourself about how would you describe the direction of this scatter plot? Is this a positive relationship? Is this a negative relationship? Or is this a lack of relationship? And then maybe start thinking about, like, does this look like a weak, a moderate, or a strong relationship? Now, we don't have a correlation coefficient. We don't have an R. But you can think about the spread of the data being sort of a proxy for R. As there's more variability, as there's more messiness in the scatter plot, then R becomes smaller, it becomes weaker. As the scatter plot has less variability, or as I like to think about it, as the relationship becomes more obvious, As the relationship becomes more obvious, R increases and we have a stronger relationship. So this is a positive correlation. We can see that as GPA increases, so does verbal SAT score. And we would draw our line of best fit like this, right? So it's oriented this way. Although I'm realizing now that I'm doing this in a camera, it's opposite, right? I should be doing it like this. I think cameras are confusing. So follow my laser pointer, right? We have the line of best fit right here. And I would call this a moderate to strong relationship. There's some variability, but the nature of the relationship is relatively obvious, right? It's not ambiguous. It's easy to tell that this is a positive correlation. What about this one? We have number of missed classes and exam score. So think to yourself, is this positive? Is this negative? Is this a lack of a relationship? If it's positive or negative, does this look weak, moderate, or strong? So take 2 seconds and think about it. So we're looking at a negative correlation. That's kind of roughly our line of best fit. And I would call this pretty strong, right? There's not a lot of ambiguity here. All of the data points are really close to our estimated line of best fit. Right? There's not a whole lot of spread. There's not a whole lot of variability. This looks pretty clear, pretty obvious. So I would describe this as a strong negative correlation. And of course here, birth month, right? If we pretend like, January is 1 and December is 12 versus height, we can see that there's no relationship, right? Our line of best fit would actually just kind of be a horizontal line. That's how you would draw it. It would have no tilt to it. So you can think about, tilt indicates a relationship. So if there's no tilt, then there's no relationship. If there's tilt, then there is a relationship. So now let's focus on eyeballing strength. Here to both the left and the right, you see two negative correlations. You see two negative associations in the scatter plots, right? As one variable decreases, the other one increases. And so we can compare these not on their relationship because they're both negative. Right? They're oriented like this. But we can notice that the scatter plot on the left, the values are tighter. And so we might call that a stronger negative correlation versus the scatter plot on the right, where the data points are spread. It's more ambiguous, right? The nature of the relationship is obvious in the scatter plot on the left, and it's less obvious in the scatter plot on the right. There's some messiness to this scatter plot. So to put it another way, here the variables are age and testosterone levels. So there's lots of variability because you can be 30 and have very low testosterone or very high testosterone, right? It's highly variable. You can be 60 and have very low testosterone or very high testosterone. So we could say on average, as I believe this is men, that would make sense. As men age, not that only men have testosterone, women have testosterone too. It just makes more sense to talk about it for men because testosterone does decrease over time substantially for men. As age increases, on average, testosterone decreases, but it's messy, right? It's not a perfect relationship. Versus here, our variables are on the left, on the y-axis, infant mortality. So the number of infants who die per 1,000 births. And on the x-axis, we have percent of adult females who are literate. This is also a great example of correlation does not equal causation. So a female adult literacy, right, from 0% to 100%, and then infant mortality. So we have a strong negative relationship, right? Everything is really tight around the line of best fit. And so this tells us that in countries with low female literacy, you also have high infant mortality. Notice it's inverse, right? As literacy is low, infant mortality is high. And then as literacy is high, infant mortality is low. But women being able to read doesn't cause infant mortality to change, right? What's probably happening here is that in countries with high female literacy, they also have probably better infrastructure systems, right? So high female literacy means that you have good education, right? That your education infrastructure and systems are pervasive and effective. And so if you have a pervasive and effective education system, you probably have a pervasive and effective health system. And so as literacy increases, infant mortality decreases. Also, as literacy increases, just in general across countries, we find that female autonomy and mobility increases, right? As adult female literacy increases, prospects for jobs and employment and income increase for women. And when that happens, we know that health outcomes are better for women and for everyone as well. So it's a good example of a strong negative correlation. It's also a good example of correlation does not equal causation. Here we have a positive example. We can see on the left another strong, tight relationship with the line of best fit. And on the right, a messy relationship. You would actually be, you might be tempted to call this a lack of a relationship. We see here on the right that we have a weak positive relationship, such that you might actually be fooled into thinking that this is a lack of a relationship. So we can then think about visualizing these correlations again as strong negative, weaker negative, no relationship, weaker positive, stronger positive. So take a second and using our two dimensions, both strength and directionality, please describe this relationship. So is it weak? Is it moderate? Is it strong? Is it positive? Is it negative? Or is there no relationship, right? Sorry, there's that third option. And here, it's a little ambiguous. I would describe this as a weak positive relationship. So if we drew our line of best fit, it's going to be something like this, right? That on average, it's sort of moving that direction, but there's lots of variability. There's lots of messiness. Take a minute and think about this one. So I would describe this as a negative relationship, right? As one value increases, the other decreases. And it's pretty strong, right? This is probably moderate to strong, is how I would describe this correlation. There's some messiness, but the relationship is obvious. And here, how would you describe this correlation? I would describe this one as no relationship. Right? Our line of best fit is going to just be a horizontal line here. Okay, so that's it for part one. When we pick up part two, we will be interrogating association claims. So now that we know about correlations and we know how to describe them, we know why they're important, we know how to use them, and we know that they reflect association claims. Part 2 is going to be about if someone makes an association claim, if we're presented with an association claim, how should we break it down? What questions should we ask in order to better understand that claim and thus better understand what we should do with that claim? Should we throw our support behind that claim, or should we question that claim? Thanks, everybody, and I will see you next time.